So, hello everyone. I'm Gitanjali. I'm a PMR scholar from IIT Delhi. So, I welcome you to the live section of quantum mechanics course. So, in this section, I will solve some of the problems that is related to hydrogen atom and identical particle. So, this problems will help you uh, understand the concept better and as well as to solve the weekly assignment. Uh, so let's get started. So before starting the problems, let me explain some of the basic details of hydrogen atom. So we know that hydrogen atom is a two-particle system. So it consists of one proton and one electron that are bonded by Coulomb potential. So the Coulomb potential is given by uh, this equation, which is minus a square by 4 pi epsilon r. And here you can see the Coulomb potential is inversely proportional to the radial part. So for this kind of potential, instead of solving this potential in Cartesian coordinate system where we use x, y, z, we solve this potential in the spherical polar coordinate system, which is nothing but the conversion of Cartesian to polar coordinate system. So in this diagram, this is the conversion for the Cartesian to polar coordinate system. So here you can see. So the z part of the polar coordinate you can write as z equal to r cos theta, and x part you can write it as r sin theta cos phi, and the y part you can write it as r sin theta tan phi. So in Cartesian coordinate system, you use x, y, z, but in polar coordinate, you use r, theta, and phi. R is nothing but the distance of the particle from the origin of the coordinate system. And so for this kind of Coulomb potential, you solve the uh, solve the problem using the spherical coordinate system. So you know that in Cartesian you use XYZ, but in polar coordinate you use R, theta, and phi. So now if you solve this hydrogen problem in spherical coordinate system, what you get is this kind of eigenfunction. So the eigenfunction of this hydrogen atom, it can be represented by psi NLM r theta phi, and it is a multiplication of two parts. One is the radial part, which is RNLR, and another one is the angular part, which is the spherical harmonics, which is YLM theta phi. Okay, so this NLM are the quantum number that is used to distinguish between different energy state of this hydrogen atom. N is the principal quantum number, L is the azimuthal quantum number, and M is the magnetic quantum number. So now for this kind of system, if you solve the commutation relation, what you got is that you see that the Hamiltonian commute with L square, which is that is why L square commutation relation is 0, as well as it also commute with Lz, and L square, L square commute with Lz. So now if you see this relation, if their commutation relation is 0, you know that you can have a common eigenstate for this kind of operator. So we conclude that the H, L square, Lz, they can have a common eigenstate, which is nothing but psi NLM R, which is this one, which is the multiplication of radial part as well as the angular part. So and L square is, it is the square of the orbital angular momentum, which is Lx square, Ly square, Lz Lz square, and Lz is the z component of orbital angular momentum. So the and this is the eigenvalue equation. Uh, in the previous page, you see that the commutation relation of H L square, H L Z, and L square L Z is 0. That means they have a common eigenstate, and when psi, which is psi NMR, and if H L square and L Z acts on it, then you will get the same eigenstate with some eigenvalue. So these are the so this is the eigenvalue equation. So if H acts on psi NMR, so it will give eigenvalue En with same eigenstate psi NLMR. And if L square acts on this eigenstate, it will give eigenvalue L into L plus 1 H squared square psi NLMR. And if Lz acts on this psi NMR, then it will give the eigenvalue mh cut with same eigenstate. So between this operator, this L square and Lz, they primarily act on this spherical harmonics part. So so you can directly write instead of psi NLMR, you can write it as this equation where L square acts on the spherical harmonics YLM theta phi and gives the same eigenvalue L into L plus 1 H cut square, and Lz when it act on this eigenstate, then it will give MH cut YLM theta pi. So you see uh, three different kind of principal quantum number. One is N, one other one is L, and the third one is M. So the M is the value for M is we get it from L. So by solving the quantum mechanics equation, you see that if for a given value of L, the value of M, it ranges from minus L to plus L in steps of 1. Okay. So other than these operators, we also have two new operator that are ladder operator, and this ladder operator are represented by these two expression. One is L plus and other one is L minus. So L plus, as you see the symbol, it is a kind of raising operator. So it raises the quantum state of the system. So this is the expression for the raising operator, which is Lx plus ILy. Similarly, for lowering operator, you have this kind of expression Lx minus ILy. So raising operator, it does what it does is it take one state M and it changes to M plus 1. Similar to lowering operator, when it acts on a state, it changes its magnetic quantum number. Let's say we have a state with magnetic quantum number n. Then after when the lowering operator acts on it, then it gets changed to m minus 1. So and these are the uh, equation that shows how the state changes after this ladder operator acts on a states, let's say psi NLM. So so when it acts on this system, you will get h cut root over of L plus 1 minus M plus 1 with a different kind of state where the magnetic quantum number get changed to M plus 1. Other quantum number remains unchanged, only the magnetic quantum number get changed. So similarly, when the lowering operator, when it acts on this psi and NMR, then you got this value h got root over of L plus 1 minus M minus 1 with a different state where the magnetic quantum number get reduced by a factor 1. So instead of M, now you have M minus 1. So these are some of the concept that is basic concept that is related to hydrogen atom. So now let's start solving some of the problems. So this is one of the problem that was not solved in the previous live section. So let me quickly solve this one. So it is given the motion of a particle of mass m in one dimensional is described by Hamiltonian h. So Hamiltonian is given. This is nothing but p square by 2m plus half m omega square x square plus lambda x. So Hamiltonian is given. So now it is asking what is the difference between the quantized energies of the first two levels. Note in the following, x is the expectation value of x in the ground state. So what is given to us? Hamiltonian is given to us. And if you see the Hamiltonian, then it contains one kinetic energy term and another one is the potential energy term. So now if you see the potential energy, it is nothing but half m omega square x square plus lambda x. So now if you see that it is a kind of perturbed potential. That is instead of ideally we see the harmonic potential is half omega square x square. But now in addition to this, we have one linear term of x, which is lambda x. So in this kind of situation, what we have to do? You have to change the coordinate system. Okay, so we have to change the expression of this potential such that you get a new type of potential energy that is similar to the old potential energy, and you can solve this problem easily. So for that, what we can do? So you see there is a x square term here, there is a x term here. So we can add a constant and also subtract a constant so that you can get a plus b squared kind of term, and that will be similar to the old potential. Okay, so let's solve it. So this is half m omega square x square plus what here you can do is first let us factor out the constant term, which is half omega square x square plus lambda x 2 by m omega square. So now this one, this is x square, this is 2 times x times a constant, which is lambda by m omega square. So now what you have to do, you have to add a constant, also subtract this constant so that the resultant term is unchanged. So now these three terms, you can write it as x plus lambda by m omega square whole square. It is a plus b whole square. And there is one another term, which is this one. This is lambda square divided by m omega square whole square. So now the Vx is nothing but half m omega square. And there is x dash square, where x dash is nothing but x plus lambda by m omega square. And there is a constant term, which is minus of half m omega square lambda by m omega square whole square. So now you are saying that this is the new potential energy is, it is similar to the potential energy that we solved before, half m omega square x square, and there is a constant term here. So for this type of potential, the energy eigenvalue, you can write it as n plus half h cut omega, which is the one that you see before, like for b of x equal to half omega square x square, you got energy is n plus half h cut omega. So now, in addition to this n plus half h cut omega, there is a constant term here. So the resultant energy eigenvalue will be this term minus the constant term. Okay. So this is the final expression for the energy eigenvalue for this kind of potential, where V of x is half omega square x square with one linear term of x. So now it is asking about what will be the energy difference between fast excited state and the ground state. Okay. So the first excited state, you know that E, it will be 1 plus half h cut omega minus this constant term lambda by m omega square whole square minus the ground state will be n is 0. So it will be half h cut omega and the minus will become plus the constant term. Okay, so the constant term will get cancelled because it's the difference between two energy level. So what you got is h cut omega. So the answer will be h cut omega. So this information, that is the expectation value of x, this is not required for this problem. So the answer will be D, h cut omega. So whenever you are seeing this kind of potential, try to solve using this kind of method. So using this kind of method, you can also calculate what is the energy level of different state and the energy difference also. So now let's solve some of the problems that is related to hydrogen atom as well as identical particle. Okay. So in this problem, it is asking what is the probability of finding the 2s electron of hydrogen atom at a distance of a0 from the nucleus and at a distance of 2a0 from the nucleus. So it is asking about what is the probability of finding electron. So in hydrogen atom, there is a proton and there is a electron which is bonded to it by Coulomb potential. So it is asking about what is the probability of finding this electron A0 from the nucleus and 2A0 from the nucleus. So for this, what you have to do is you have to calculate the radial probability density. So the radial probability density, it is given by R square and RLM R square. So this R and R will be given to you. So this expression for R and MR is this one. So this is the, so here you can see R for 2s. So for 2s, N is 2 and for S, L is 0, right? So R and L is nothing but R 2 0. So the expression, this expression will be given to you. So R20 is this. So what you have to do is you have to calculate the radial probability density, which is R square multiplied by this probably this radial part. So now the final expression is this. So you got this radial probability density. Now what you have to do is you have to just put the value of R in this expression. So it is asking about what is the probability when R equal to A0 and what is the probability when R equal to 2A0, right? So, so in this expression, you have to just put the R equal to A0 part and R equal to 2A0 part. So now if you put this, then for R equal to A0, you will get this value, which is 0.37 by 8A0. And for 2A0, you will get the probability density is 0. So the probability of finding this electron at R equal to A0 is 0.37 by 8 A0. And the probability of finding this 2s electron at 2s0 is 0. So in this way, you can calculate the probability of finding the electron for any kind of orbital. Like in this case, I have solved it for 2s. You can also solve it for 2p, 3s, 3d, any kind of orbital. So for that, what you have to do, you have to just calculate the what is the n and l for this kind of state, and according to that, you can take the radial part and calculate the radial probability density. So this is how you can calculate the probability. So this is the third problem that is related to many particle system. So let me go through the questions one. So in the question, it is given non-interacting bosons are in an infinite potential well defined by V of x equal to 0 when x lies between 0 to a, and it is infinity for other reason. So this is given. There is a infinite 1D potential well, and the width of this potential well is a. So now it is asking, find the ground state energy of the system, and what would be the ground state energy if the particles are fermions. So bosons, let me solve for bosons first. So bosons are nothing but the particles that have spin is equal to 1. So this kind of particle, they do not follow Fermi-Dirac statistics. So Fermi-Dirac statistics is kind of it's kind of a distribution of particle in different energy level. So if a particle like fermions, they follow Fermi-Dirac statistics, but bosons, they follow Bose-Einstein statistics. So these Fermi-Dirac and Bose-Einstein, these are nothing but the way you fill up the particles in different energy level. So when you have Bose-Einstein statistics, so what you say is that these mini particles you can if you have, let's say you have n different bosons and different boson particle, then you can place it on the same energy level. So different particles can occupy the same energy level. But if you have fermions, then fermions, they follow Fermi-Dirac statistics. So in that case, the state will be occupied by only two particles. These two particles have two different spin. Okay, so let's say now we have a 1D potential well. So 1D potential well, you have different kind of energy level which have energy En equal to h cut square pi square by 2m a square n square. Here n is 1, 2, 3. So when the particles are bosons, then you can place all the boson in the same energy level. Like if they are asking about ground state, then you can place it on the ground state. All the particle in the same ground state, E1. Okay, so let me show you clearly. So if you have bosons, now you have n non-interacting bosons. So for this case, if you have potential like this, which have different energy level, So now you can place all the boson particles in the same ground state, in the ground state only. Okay, all these n particle can occupy the ground state energy. So that means the energy of this system, the ground state energy of this system will be n into the ground state energy of this level, the energy of this level, which is nothing but n into h square pi square by 2m a square and 1 square. N is 1. So that means the ground state energy of a system which is n non-interacting boson particles will be n times h square pi square divided by 2m a square. This will be the case when the particles are bosons. Now let's see what will happen when the particle is fermions. Okay, so fermions, let's say electron. So electrons are fermions, they are spin-up particle. So in this case, what happens? They follow Fermi-Dirac statistics, and according to the Pauli exclusion principle, one given quantum state will be occupied by two fermions, which have which have different spin quantum number. Okay, so now what we have is fermions. So n, instead of n bosons, now you have n fermions. So in this case, the distribution of energy level is like this. So the first state will be occupied by two fermions. Next state will be two fermions. Likewise, it will be filled in this manner. Okay. So now for this kind of particle distribution, the ground state energy will be 2 into the ground energy of this level plus 2 into energy of this E2 level plus 2 into energy level of this level, right? So if you have n fermions, that means n by 2 state will be occupied. So now you can understand it by using, let's say, by taking an example. Let's say we have n equal to 4, right? So n equal to 4 means the first state and the second state will be occupied. So that means two energy levels are occupied, which is n by 2. In when n is odd also, if n is 3, then that in that case also n by 2 energy levels are occupied. And what happens in that case is only the last energy level is occupied by one particle. So in this case, for this case, when it is even, all particles are paired. All energy levels have two particles. Or when n is odd, the last energy level will have only one particle. So that means the energy level, ground state energy level for this composite system, you can write it as 2 into E1 plus 2 into E2 plus 2 into E n by 2. Okay. So now you just have to put the expression for the energy level, which is h square pi square 2m square. Here n is 1, so 1 square 2 square, 3 square, da, 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 and the last state is n by 2 square. So this is, this is nothing but 1 by 6 n by 2, n by 2 plus 1, and 2 into n by 2 plus 1. So that means it is h square pi square by ms square divided by n into n plus 1, n plus 2 divided by 24. So now you are saying for fermions the ground state energy is this, but when you have bosons, the ground state energy is different, which is nothing but n h square pi square by 2ms square. So if you have different kind of particles, then ground state energy will be different. Okay, now if you have bosons, then you can put all the particle in the same energy state. But if you have fermions, then one state will be occupied by, let's say for spin up particle, it will be occupied by two particles which have different spin quantum number. Okay. So, do you have any doubt or the problems I have solved till now? Otherwise, I can proceed. Okay, so let's see our second problem. The second problem is energy of the first excited quantum state of a particle in the two-dimensional potential, which is given this is. So it is a uh, multi-dimensional problem. It's for this problem it is two-dimensional. So it is given a particle is inside a 2D potential. And the potential of this two dimension is Vxy, which is half m omega square x square plus 4y square. Now it is asking about what will be the energy of first excited state. So this is similar to a harmonic potential in 2D. So now if you separate out the x and y term, this is 4y square. This second part you can write it as m 4 omega square y square. That means it is half omega square x square by half m 2 omega square y square. Right? So now the particle is inside this 2D harmonic potential. So for 1D, we know that the energy is n plus half h cut omega. For 2D, the energy eigenvalue can be written as nx half h cut omega x plus ny half h cut omega y. Now if you compare this potential, then what you will see is the omega x is omega here and omega y is 2 omega here, right? So that means you can take the energy of this composite system as nx plus half h cut omega plus ny plus half 2h cut omega. Now it is asking about the first excited state. So the ground state, what will be the energy for ground state? So for ground state, this Nx will be 0 and Ny will be 0. That means it is half h cut omega plus half into 2 h cut omega, which is nothing but 3 by 2 h cut omega. Now for the first excited state, what you can have is either one of this Nx and Ny is non-zero and other one is 0. That is either Nx equal to 1 and Y equal to 0, or either Nx equal to 0 and Y equal to 1. Right? So now you have to see which one will give the first excited state energy eigenvalue. In this two, which one will give the next highest energy level, which is greater than 3 by 2? So let's now if you see this omega y is 2 omega, omega x is omega. So that means if you take nx equal to 1 and ny equal to 0, then you will get the next highest energy level. If you take nx equal to 0 and ny equal to 1, then for that case the energy will be higher. It will be higher than 3 by 2 h cut omega, but it will be uh, higher than the first excited state. So let's see what is the energy we will get. Let's say the first one is nx equal to 1 and y is 0. So that means it will give 1 plus half h cut omega 1 plus half, which is nothing but 3 by 2 h cut omega, and the other one is nx is 0 and y equal to 1. This will give 1 plus half into 2 h cut omega 3 by 2. This will give 3 h cut omega. Now I think this ground state, let me check once again. This is 2 omega. This is 3 by 2. But this will give 3 by 2 h cut omega, which is nothing but the energy of this. It is similar to the ground state energy, right? Wait. Zero and this is 1. Zero, zero, it should be 3 by 2. This one. And for nx equal to 1. Okay. Okay. So there is one term is missing here. Nx equal to 1. So it is 1 plus half h cut omega, and there is another term that I have not shown. Ny is 0, right? So this will be 0 plus half 2 h cut omega. So that means this is 5 by 2 h cot omega. This is now 3 by 2. I have not shown, I have missed this term while calculation. So this is 5 by 2 h cot omega. This is 3 h cot omega. So that means this is the first excited state energy. And this will be the second excited state energy. And this is the ground state. Okay. So let me solve the next question. So it is given a particle of mass m in a cubic potential of box A, and the potential inside the box is it is given x, y, z. It is 0 when x lies between 0 to a, y lies between 0 to a, and z lies between 0 to a. Is 0 and infinity outside. So now it is saying if the particle is in the eigenstate energy, this. So it is telling us that the energy eigenstate of the particle is 14 pi square h squared square divided by 2m a square. Now it is asking about what will be the wave function of this particle in this 3D cubic potential. So for 1D we know that the energy is h squared pi square divided by 2m a square n square. So now when we are talking about a particle in 3D, then this energy can be written as h squared pi square 2m a square nx square plus ny square plus nz square. So it is the summation of the energy 3 dimension. Okay. So let me make a comparison. So in 1D and there is 3D. So in 1D we have energy square pi square by 2m square n square. So in 3D this will be h square pi square 2m square nx square plus ny square plus nz. Similar to the wave function, here you have wave function as root over of 2 by a sine n pi by a into x. So in 3D, what you have is the product of these terms in x, y, and z direction. So it will be root over of 2 by a sine n pi x by a root over of 2 by a sine n pi y by a multiplied by root over 2 by a sine n pi z by a. Okay, so that means it will be 8 by a cube sine n pi x by a sine n pi y by a and sine n pi z by a. So what is given to is the energy of this particle in 3D, which is 14 pi square h square divided by 2m a square. So this is given to you. Now it is asking about the wave function. So options are already given to you. Now, if you compare this energy to this one, this means nx square plus ny square plus nz square equal to 14. So now what you have to do is we have to look for nx, ny, nz in the option that will give nx square plus ny square plus nz square equal to 40, right? So the options are already given. You just have to check. So if you check the first one, this one, then the nx is 3, ny is 5, and z is 6. This is nx, this is 5, and this is 6. So now if you add this square of this nx, ny, and z, then it will not be 40. It will be greater than 40, right? Now if you see the second one, is 7, 4, and 3. 7 square is already 49, so it will not be 14. The third one is 4, 8, 2. It is also because 8 square is already 64. So the summation will be greater than 14. And the last one is nx is 1 and it is 2 and 3. So that means this is 9 plus 4 plus 1. So it is 14. Right? So that means the answer is D. Okay. So these are the problems that is related to multidimensional particle in a multidimensional box or harmonic potential also. So let's see our next question. So it is based on the hydrogen atom problem. Let me go through the question. Let psi NLM denote the eigenfunction of a Hamiltonian for a spherically symmetric potential P of R. The wave function psi is given by this is an eigenfunction of. So it is telling psi is given, which is 1 by 4 psi 210 plus root over of 5 psi 21 minus 1, so root over of 10 psi 21. So now it is asking about whether this psi is an eigenfunction of h, L square, and Lz. So for that, what you have to do is you have to check whether when h acts on this psi, whether it gives the same eigenstate or not. That is some constant multiplied by the same eigenstate. You have to check this one. Also, you have to check whether L square psi gives some constant C2 psi or whether Lz when acts on psi, whether it is giving some constant the same eigenstate. So let me solve this one. It's psi. So psi is already given is 1 by 4 psi 210 plus root over of 5 by 4 psi 21 minus 1 plus root over of 10 by 4 psi 21. Right? Now if H acts on psi, you know that when H acts on psi NLMM, it will give En psi NLM. Right? That means H psi will be 1 by 4. Here you see N is 2 here. Here is also N is 2. Here N is 2. That means it will give 1 by 4 E2 psi 210 plus E2 psi 21 minus 1 plus root over of 10 by 4 E2 psi 211. So E2 is present in all the terms. That means you can factor it out. Root over of 5 by 4 psi 2 1 minus 1 plus root over of 10 by 4 psi 2 1 1. So this gives E2 times psi, right? So this is a eigenvalue equation. H psi gives E2 psi. So that means H is an eigenfunction of psi, right? Similarly, for L square, when it acts on psi, so this will give, you know that when L square acts on psi NLM, it will give L into L plus 1, its got square psi NLM, right? This is, you know. So what you have to do is, you have to act L square on this superposed state. So this will give 1 by 4. If you see this equation, so if you see this one, then L is 1 here, this one L is 1, this one also L is 1, right? That means it will give 1 by 4 L into L plus 1. When L equal to 1, L into L plus 1 will be 2. This will give 2h squared square psi 210 plus root over of 5 by 4 2h squared square psi 21 minus 1 plus root over 10 by 4 2h squared square psi 211. So this means this 2h squared square is also present in all terms. So you can factor it out. So what will remain is 1 by 4 psi 210 plus root over 5 by 4 psi 21 minus 1 plus 10 by 4 psi 21. So if you see this one, this is nothing but the psi, right? That means when L square acts on psi, it gives 2h squared square times psi. So this means psi is also an eigenfunction of L square. Similarly, for Lz, you can also solve. Lz, you know that Lz, when it acts on psi NLM, it gives MH cot psi NLM. And so what you have to do, you have to see what is the value of M in each term. According to that, we have to solve it. So let me solve this one. Then I will tell you one of the shortest way to find out this kind of problem. So let me write down the psi first. So psi is 1 by 4 psi 210 root over of 5 by 4 psi 21 minus 1 root over of 10 by 4 psi 21. So if you see the first one, then here M is 0, here M is minus 1, here M is 1. So that means when Lz acts on this one, it will give 0h cot. When Lz acts on this one, it will give minus h cot to root over of 5 by 4. And when it acts on this one, it will give h cot root over of 10 by 4. So that means there is a state here also, psi 2 1 minus 1, here psi 2 1. So that means this is the resultant state is A minus H cot psi 2 1 minus 1 minus root over 10 by 4 psi 2 1. So if you see there is a term missing here which is psi 210. That means it is not equal to the same state psi with some constant. So that means this eigenfunction is not compatible with Lz, but it is compatible with H and L square. Okay. So the answer will be HL square only. This one. So the shortest way to find out means to see whether one is y eigenfunction of H L square or Lz when you are given a superposed state is, let's see what was given to us. It was given the psi is 1 by 4 psi 210 plus root over of 5 psi 21 minus 1 plus root over of 10 psi 211. So first what you have to do, you have to see what is the NLM for this eigenstate. So here n is 2, L is 1, M is 0. Here n is 2, L is 1, M is minus 1. Here n is 2, L is 1, M is 1. So if you see the NLM for this eigenstate, you see that the N and L are same for all these three eigenstate. Only the M is different. So that means the H and L square will be an eigenfunction of psi. Okay, H and L square uh, will be eigenfunction of psi because the n is correspond to H and L correspond to small l correspond to L square. And for Lz, the quantum number related to Lz is m. Now you are seeing that the m are different for this superposed state. So that means this psi will not be eigenfunction of Lz. Okay. So if you see, so if you're seeing that n are same for all superposed state, that means H will be an eigenfunction. If L is same, that means L square will be an eigenfunction. If Lz is same, that means Lz will be an eigenfunction. In this way, you can check whether the state is an eigenfunction of operator H, L square or Lz. So till now, do you have any doubt related to the problem I have solved? If you have any kind of doubt, then you can ask me. Okay. So not then, let me solve the next problem. So it is given the wave function of a particle of hydrogen atom is given by this. Is given psi of a particle is a superposed state of psi NLM psi 3 psi 210 plus root 2 psi 21 minus 1. And it is given psi NLM is the normalized eigenfunction of the state with quantum number NLM in the usual notation. Now it is asking the expectation value of Lz in the state psi. It is asking about the expectation value of Lz in the state psi. So you know that the expectation value is nothing but psi Lz psi divided by psi psi, right? If you see, so first what you have to do is you have to normalize this state. So you see that it is not normalized. So what you have to do, you have to multiply it a normalization constant that will give psi psi equal to 1. That means it will be c square 1 plus 4 plus 9 plus 2 equal to 1. It will be 16. So c will be 1 by root over of 16. This is the normalization constant. So that means psi equal to 1 by root over of 16 psi 200 2 by root over 16 psi 211 plus 3 by root over of 16 psi 210 plus 2 by 16 psi 21 minus 1. So when you have a normalized state, the expectation value, you can directly write it as summation of probability multiplied by eigenvalue. Eigenvalue of Lz in psi. So let us first calculate what is the eigenvalues of Lz in this state psi. So psi is given as, this is the state given. If you see the first term, then m is 0, second term m is 1, third term m is also 0, last term m is minus 1. So that means when Lz will act on psi, it will give three values. One is, which is mh cot, so it will give 0 h cot, 1 h cot, and minus 1 h cot. Now the probability of getting 0 h cot is nothing but the square of this coefficient, that is with m equal to 0. This is 1 by root over 16. We are seeing a term 1 by root over 16. And there is a term 3 by root over 16. So that means it will be 1 by 16 plus 9 by 16. And probability of getting 1 h cut is square of this coefficient, this one. We are saying m equal to 1 here, so it will be square of this coefficient. So it will be 4 by 16. And for the last one, the probability is square of this term, so it will be 2 by 16. So now the expectation value is probability multiplied by eigenvalue. So for 1 h cut, probability is 4 by 16 multiplied by 1 h cut, and for minus 1 h cut, the probability is 2 by 16 multiplied by minus h cut. So that means this is already 0 and this is 2 by 16 h cut, right? So it will be h cut by 8. So when you are given a state, first try to normalize it, and after normalization, you can directly write the expectation value as a summation of probability into eigenvalue. And the probability you can get it from the coefficient. Eigenvalue, for that you have to see the uh, quantum number. So the answer will be this one, which is h cut by 8. So I think this problem is clear to you. Let me see the next problem. So let's see what is given to us. So it is given the unnormalized wave function of a particle in a spherically symmetric potential is given by this. So wave function is given, which is z f of r, where f of r is a function of a radial variable r. Now it is asking the eigenvalue of the operator L square is. So a wave function is given. Now it is asking about what will be the eigenvalue of operator L square. Okay, so you know that the eigenfunction of L square is psi n m r equal to L into L plus 1 h cut square psi lemon r. So this is the eigenvalue. Now this wave function is different from this psi n m n r. It is not written in this standard form. So first what you have to do is we have to write it in this standard form. So it is given z times f of r, right? So now you know that in spherical polar coordinate, which you represent like this. This is theta, this is r, there is one other variable phi. So for this, z is r cos theta, right? That means here z is r cos theta times f of r. So you are saying this is r f of r cos theta, right? So this is the radial part, and this is one term which is related to spherical harmonics, which is y l m theta phi, right? So in during the starting of this section, I told you that this L square typically acts on this spherical harmonics of this psi Lm, and it gives L into L plus 1 h cut square. So that means when L square acts on this psi of r that is given to us, it will not act on this radial part, but it will act on this cos theta, right? It will act on this cos theta. So what you have to do is you have to compare this YLM with the standard form. So YLM is cos theta, right? This is the radial part. This is the spherical harmonics. So this means this is YLM theta phi. So if you compare this YLM to the standard form that is given in the textbook, you see that it is related to Y 10 theta phi. Okay, for y10, it is this y10 is directly proportional to cos theta. So y00, I think it is a constant term which is root over 3 by 4 pi, I think. And y10 is some constant term multiplied by cos theta. So that means this for cos theta, this is y10, that means L equal to 1, M equal to 0. Right? So that means you got the value of L. Now when this L square will act on this y10, it will give L into L plus 1 h cut square multiplied by the same state. And L is 1 here. So that means this is 2 h cut square. So that means this is the eigenvalue. Right? So for this kind of problem, you just have to convert the Cartesian to polar coordinate, and you have to compare this spherical harmonics with the standard form to get the value of L and I. So in this way, you can solve this problem, and the answer for this problem is 2h cut square, which is D. So I think this problem is clear to you. If not, you can ask me anytime if you have any doubt. Okay, so let's see our next problem. So next problem, it says psi NLM denotes the eigenfunction of the Hamiltonian with a potential V of R. Then the expectation value of the operator Lx square plus Ly square in the state. This. So it is asking about what will be the expectation value of Lx square plus Ly square when you have state psi equal to 1 by 5 is psi 211 plus psi 210 to the power of 15 psi 21 minus. So whenever they are asking about expectation, first we have to check whether the state psi is normalized or not. So if you check, then this will be 3 by 5 square plus 1 by 5 square plus 15 root over 15 by 5 square. So this is 9, 1 and 15. So this is normalized. So that means the expectation value, you can write it as a summation of probability multiplied by different eigenvalue. But this L square, Lx square, Ly square expectation, eigenvalue you don't know. But what you know is L square eigenvalue when it act on any normal eigenfunction psi NLM, it gives L into L plus 1 h cut square and you know the expectation will know the eigen value of this LZ, which is MH cut psi NLM R. So what you have to do is, you know that L square is Lx square plus Ly square plus Lz square. That means Lx square plus Ly square will be L square minus Lz square, right? So instead of calculating the expectation value of Lx square, Ly square, what we can do, you can calculate the expectation value of L square and Lz square because they are equal. So if I have to calculate if this Lx square Ly square expectation, that will be equal to L square Lz square expectation. So this will be L square expectation minus Lz square expectation. Now this L square expectation, you can write it as summation of probability multiplied by eigenvalue, right? So what we have to do is we have to find out the NLM for the superposed state. So the superposed state is 1 by 5, 3 psi 2, 1, 1, psi 2, 1, 0 minus root over of 15, psi 2, 1 minus. So that means if you see this one, for L square, what you have to find out? L. For Lz, you have to find out M. So let's see the value of L. Here L is 1, L is 1. Here also L is 1. Right? Means everywhere, for every eigenstate, it is 1. So that means L into L plus 1 h squared square, you will get 2 h squared square. Right? So that means L square expectation value will be 2h squared square multiplied by probability. So 2h squared square is everywhere. That way it will be summation of probability. 2h squared square multiplied by summation of probability. The summation of probability will be 1 because the psi is already normalized. This is 2h squared square. So one term you get in this term is this one is 2h squared square. Now for Lz, what you have to do, you have to find out the value of M. So if you see this one, M is 1. For this one, M is 0. For this one, M is minus 1. That means the eigenvalue for Lz you will get 0 h cut, 1 h cut, and minus 1 h cut. So that means the Lz square expectation will be summation of probability and eigenvalue square because it is Lz square, right? So you will get square of mh cut square. So probability you will get from the coefficient for m equal to 1. You are saying that the coefficient is 3 by 5. So that means it is 3 by 5 square h cut square. For 0 h cut, you will get some probability that is 1 by 5 square multiplied by 0 h cut square. And for minus h cut, you will get the coefficient as minus root over of 5 root over 15 by 5 square multiplied by minus h cut. When you take the square, it will be h cut only. Right, it will be 9 by 25 h cut square. It will be 0, this one. And this is 15 by 25 h cut square. That means it is 24 by 25 h square. So the Lx square plus Ly square expectation will be given by this. And this one you get 2 h cut square. The second one is 24 by h cut square by 25. So this will give 26 by 25 h cut square. So this is the answer. So when you are given the expectation value of Lx or Ly, try to express it in terms of L square and Lz. Because L square, Lz eigenvalue you already know. So if you can relate this to, then you can easily find out what is the eigenvalue as well as the expectation as well as the probability. So the answer will be 6 D 26 h cut square by 25. This problem is also similar to the previous problem. It is real. Here we have to also find out what is the expectation value of L square as well as the expectation value of energy. So let's see what is given to us. So it is given the wave function for a hydrogen atom is given by following superposition of energy eigenfunction. So psi of r is given, which is nothing but root over of 2 by 7 psi 100 r e by root over of 50 psi 210 r and 1 by root over of 40 psi 322 r. Now it is asking about the ratio of expectation value of energy to the ground state energy and the expectation value of L square. So let us first calculate what is the expectation value of L square. Okay. So first what we have to do is we have to see whether psi of r is normalized or not. So so let's see psi of r is psi of r. So this is nothing but root over of 2 by 7 square 3 by 14 root over 14 plus 1 by root over 14 square. So this means this is 2 by 7, 9 by 14, 1 by 14. So this is nothing but 1. So that means this one is normalized. So you don't have to normalize it. Now for the expectation, as I said, the expectation of L square you can write as a summation of probability with the eigenvalue. So first we have to see what is the eigenvalue of L square in the superposed state. So psi of r is given. This is root over 2 by 7 psi 100 3 by root over 14 psi 210 plus 1 by root over 14 psi 322. So let's see what is the value of L. Because L square is related to L. The quantum state that is related to L square is L. So let's see what is the value of L. This is 0. This is L equal to 1. Here L is 2. Right? So that means The eigenvalue you will get for this one is 0. This is 2h cut square. This is 2 into 2 plus 1, 6h cut square, right? So L square expectation will be 2h cut square multiplied by its probability, which is the square of this term, plus 6h cut square multiplied by probability, which is 1 by root over of 14 square. So if you solve it, you will get around 12 h cut by 7. So, so for the expectation, you calculate, it will come out as 12 h cut square by 7. Now, if you see in the option, there are two option that have 12 h cut square by 7. So for that, we have to calculate the first one. Okay, that is the expectation value of energy. Now the next one is asking about what is the ratio of expectation value of energy to the energy of ground state. So for energy, what you have to see, energy, you know that it is minus 13.6 divided by n square electron volt. So that means it is related to n, the principal quantum number. So that means we have to see what is the value of n in our problem. So for this one, for this state, n is 1. For this state, n is 2. For this state, n is 3. So n we have 1, 2 and 3. That means we will get 3 different kind of energy, which is E1, this is E2, this is E3. So that means the expectation value of energy will be summation of probability multiplied by eigenvalue So if you see the superposed the state psi, then it is 2 by 7 psi 100 3 by root over 14 psi 210 is 1 by root over 14 psi 322. So the expectation value of energy will be here n is 1. So that means it is E1 multiplied by root over 2 by 7 square plus here n is 2. That means it will be E2 multiplied by 3 divided by the root of 14 square. And the third one, n is 3. So it will be E3 into 1 by root over of 14 square. So E1, you know, is minus 13.6 by 1 square. So this is the ground state energy of this system. And for E2, it is the next higher state energy, which is for E2, it is 2 square minus 13.6 divided by 2 square. Similarly for E3, it is minus 13.6 divided by 3 square. That means it is E1 by 2 square. This is E2 by 3 square. So let me put this in the above this in this equation. So you will get 2 by 7 into E1 plus 9 by 14 into E1 by 4 plus 1 by 40 E1 by 9. So the final, if you add these terms, you will get 229 E1 divided by 504. So that means the ratio of expectation value of energy divided by the ground state energy E1 is nothing but 229 by 504. So you have to look for a option that will have this answer. So if you see the first one have 229 divided by 504, that means the answer is this one. So this is how you can calculate the expectation value of energy as well as the expectation value of operator. So do you have any doubt till now? Okay. Okay, then so let me go to the next question. So next question is, it is based on many body system. So it is given the lowest quantum mechanical energy of a particle confined in a one-dimensional box of size L. So there is a particle which is confined inside a one-dimensional box of length L. So it is given the lowest quantum mechanical energy, that means the ground state energy is given to us, which is 2 electron volt. Now, it is asking the energy of the quantum mechanical ground state for a system of 3 non-interacting spin-up particles. So instead of one particle, we now have 3 non-interacting spin-up particles. Okay, so now it is asking about what will be the ground state energy of this system. You are given is a system where one particle is present in a one-dimensional box and the ground state energy is 2 electron volt. Now, instead of one particle, if you have 3 particles, then what will be the ground state energy? And these particles are spin-up particles. That means they are fermions. Okay, so that means one quantum state will have uh, 2 particles that have 2 different kind of spin. Okay, so this one day potential, they have different energy level. Now, if they are fermions, then you can only put 2 particle here, not more than 2 for spin-up particle. Okay, and it is given there are 3 fermions. That means the next fermion will go to the next state that is above the ground state. So this is E1 and this one is E2. So that means, and E2 you know, E2 is nothing but 2 square times h square pi square 2m square. This is 4 times of E1, right? If it is E1, then E2 will be 4 times of E1. So that means the ground state energy will be 2 times of E1 because there are 2 particles in the E1 state and there is 1 particle in the E2 state. So this is 1 into 4E1. That means this is nothing but 6 times of E1. And E1 is given. This is the ground state energy. It is given here. So E1 given, it is, I think, 2 electron volt. No, it is 2 electron volt. So that means the ground state energy of 3 fermions, the non-interacting fermions will be 6 times of E1, will be 6 times of 2, 12 electron volt. So that means the answer will be 12, which is C. So in this way, you can solve the problems based on particles, more than one particle, to find out their energy, energy of the system. So instead of 3 fermions, if you have 4 fermions, then for that case, what you can do is you have to just put the next fermions in the E2 state, and instead of 1 into 4 E1, you will have 2 into 4 E1. Okay. So the next one is based on the simple harmonic oscillator, and it is telling there are 5 identical spin-up particles which are subjected to a one-dimensional simple harmonic oscillator. So for simple harmonic oscillator, you know that En is n plus half h cut omega for a one particle system. So now if you have 5 identical spin-up particles, spin-up means fermions. There are fermions, so one state will have 2 particles. So if these are the energy levels of uh, simple harmonic oscillator, then you can only put 2 particle here, another 2 particle here, and the next particle here. So there are total 5 particles. So this is E0, this is E1, this is E2. Now the ground state energy you can easily find out after this particle distribution, which is 2 times of E0 plus 2 times of E1 plus E2. There is one particle there. So that means 2 times of E0 is half h cut omega. 2 times of E1 is n is 1. So it will be 3 by 2 h cut omega plus E2 is 5 by 2 h cut omega. That means this will be 3 plus 4 plus 13 h cut omega by 2. This is the ground state energy of this system. Okay. So let's see our next problem. So it is given the normalized ground state wave function of a hydrogen atom is given by psi of r equal to 1 by root over of 4 pi 2 by a3 by 2 e r by a. So a is the Bohr radius and r is the distance of the electron from the nucleus. So now it is asking what will be the expectation value of 1 by r square. So for that, what you have to do, this is psi of r is already normalized. It is given normalized ground state. That means it will be the expectation value of psi of r will be psi of r 1 by r square psi of r. So that means if you write it in terms of integration, it will be I star r 1 by r square psi of r dv. And dv for the spherical coordinate, you write it as r square sin theta d theta d phi dr. So that means you have three integration. For one is for r, which runs from 0 to infinity. One is for theta, for and it will be from 0 to pi, and one is for phi. It will be from 0 to 2 pi. So this is 1 by r square multiplied by 4 by 4 pi a cube e to power minus 2 r by a r square sin theta d theta d phi. So this r square will cancel, and the integration of 0 to 2 pi d phi will be 2 pi, and the integration of 0 to pi sin theta d theta will be 2. So now what we have is 1 by r square equal to 4 into 4 pi. I am factoring out the constant. So the term which remains is e to power minus 2r by a dr. So this one you can solve. You can just substitute 2r by a equal to x. That means dr equal to a dx by 2. So this is 4 by a cube. We will get a by 2 here is 0 to infinity e to power minus x dx. This is 1. So that means this is 2 by a square. So that means the expectation value of 1 by r square is 2 by a square, just t. Okay, this is how you can solve the expectation when the psi of r is given in this form. So do you have any doubt till now in any of this problem? Otherwise, let's see the next problem. Hmm. So, okay. So this problem is based on the graphical representation of radial probability. So it is given the ground state wave function for the hydrogen atom is given by this one psi 10 equal to 1 by root over 4 pi 1 by a0 p by 2 e to power minus r by a0, where a0 is the Bohr radius. Now the plot of the radial probability density P of r for the hydrogen atom in the ground state will be. So it is asking about what is the radial probability density of this wave function. So four options are given. So let us first calculate what is the radial probability density. So the radial probability density is nothing but r square time is psi of 100 square. That means it is r square times 4 pi 1 by a0 cube e to power minus 2 r by a0. Okay. So now if you see this, let's see what will be the value of this radial probability density in the origin when r equal to 0. So when r equal to 0, you are saying there is a r square term here. So that means this radial probability density at the origin will be 0, right? Now let's see the options. So if you see in the options for other than A, other than D, if you see A, the radial probability density at the origin here, it is not 0. For this one also, it is some value here. And for this one also, it is P of R is not 0. Right? Only for this case, the radial probability density is 0 in the origin here. Right? So that means your probability density uh, graphical representation is this D. So you don't have to calculate any other value by seeing the distribution of radial probability density at the origin. We can easily find out what is the plot for this radial probability density. Right? Okay. So let's see the next problem. So this is given. The wave function of a hydrogen atom is this 1 by root over of 10 2 psi 100 plus psi 210 plus root 2 psi 211 plus root 3 psi 21 minus. It is asking about the probability of finding the system in L equal to 1 and M equal to 1. So first see whether this psi is normalized or not. So let's see. This will be 2 by square plus 1 by root over 10 square. So if you see, it is normalized. So that means the probability will be the coefficient. So you see that if you see this expression, let me write it out again. Is 1 by root over of 10 2 psi 100 psi 210 root 2 psi 211 plus root 3 psi 21 minus 1. So let's see. Now it is asking what is the probability for L equal to 1, M equal to 1. So we have to see where, for which eigenstate we have these values. So if you see this one, for this one L equal to 1, M equal to 1. For this one it is L equal to 1, but M is 0. For this one L is 0, M is 0. In this one L is 1, but M is minus. So that means the probability is nothing but the coefficient square, right? So that means it will be root over of 2 by 10 square. The probability of getting L equal to, so let me write it clearly. So probability of getting L equal to 1, M equal to 1 is root over of 10 by 8, which is nothing but 1 by 5. So the answer will be, no, there is no option. So this is the answer. Oh, so let's see our next problem. So it is asking about the expectation value of x component of orbital angular momentum Lx in the state this. So it is asking about the expectation value of Lx. What is this? When you have psi equal to 1 by 5, p psi to 1 minus 1 root over 5 psi to 1 0 root over 11 psi to 1 1. So for L square and LZ, it's easy. You just have to calculate you just have to find out what is the NLM. Uh, for L square, it is you have to find out L, and for LZ, you have to find out M. But for LX, you know that psi NLM is not a eigenfunction of Lx, right? So you have to express Lx in terms of a quantity for which you can calculate what will be the eigenfunction or what will happen when Lx acts on it. So whenever Lx is given or Ly is given, what you have to do, you have to express it in terms of the ladder operator. Okay. So ladder operator is nothing but L plus and these are L minus. These are expressed in terms of Lx and Ly. For L minus, it is minus IL. So that means the Lx will be L plus L minus divided by 2. Right? So that means the expectation value of Lx would be the expectation value of L plus L minus divided by 2. Similarly, if Ly is given, what you have to do is we have to express it in terms of L plus and L minus. Okay. So Lx is L plus L minus divided by 2. So L plus, when L plus acts on psi NLM, it gives h cut root over of L into L plus 1 minus M into M plus 1 with psi N L M plus 1. Similarly, when it acts on psi N and M, it gives psi L plus 1 M minus 1 psi N L M minus 1. Okay. So psi is already given to you. Psi is nothing but 1 by 5, 3 psi to 1 minus 1 plus root over 5 to 1 0 plus minus root over of 11 psi to 1. So when L plus, when it acts on psi, it will give. So there are 3 states, like there are 3 states. So when L plus, when it act on this one, it will give psi to 1 and the minus 1 will become minus 1 plus 1 will become psi 0. So this state will become psi 2 1. M plus 1 means 0 plus 1. So 1 and this 1 becomes psi 2 1 1 plus 1 is 2. Now when you take this uh, expectation. So you see that for this dagger also, since dagger is 1 by 5, 3 psi 2 1 minus 1 plus root over of 5 psi 2 1 0 minus root over 11 psi 2 1 1. So there is no terms 2 1 minus 2 1 2 terms here in the dagger. So that means this term will become 0 when you take the inner product. So what is the term we have to take? Only this psi 2 1 1 and psi 2 1 0. So that means psi L plus psi will be, see 2 1 1 is here, and there is a so 2 1 1. So let's see. So before calculating the expectation, let's see what will be the this state L plus psi. So this is nothing but 3 1 by 5 3. When you calculate this one for this L equal to 1 for this state, so you will get root over of 2h cut psi 210 plus root over 5. Here L is also 1 here. So you will get root over 2h cut psi 211. Okay. Now when you take the inner product, you have to see what is the coefficient of psi 210 here with the dagger. So 210, there is root over 5 by 5, right? So this will be root over 5 by 5 into this one, 3 root 2 h cut by 5. And there is a term 211. So 211 is here and there is a 211 here. So that means it will be, so there is a minus here, right? So there will be minus root over of 11 by 5, root over of 5, root 2 h cut by 5. So this is the final expression for expectation value of L plus. So if you solve it, you will get around root over of 10 h cut by 25, 3 minus root over 11. So similarly for L minus also, if you calculate in the similar manner, what you will get is, you will get the same expectation value. That means the Lx expectation will be Lx plus L minus divided by 2, which is nothing but root over of 10 h cut by 25, 3 minus root over of 11. So this is the answer. So that means this is the answer will be option A, root over of 11 by 11 minus 3. So this is the last question. Okay. So let me continue the other question in the next section. So for now, do you have any doubt in any of the problem? If you have any doubt, then you can ask me now. Otherwise, we can end this section. Okay, okay. Okay, thank you. So thank you for joining this section. I hope you understand the problems that I have solved today. So let us meet on next Saturday. So thank you.